So, also hello from my side. Today I'm presenting the work of a student of mine. She made a very good job for this topic. Martin and I, we supervised her. So, I think we all know the situation. We are in a bus on our way to work or to an important appointment, and we are stuck in traffic. We can already see the bus stop downstream the intersection, but we cannot do anything to get there faster. But today we have bus prioritization in many cities and also at most of the intersections. But nevertheless, if we are in rush hour traffic, prioritization sometimes still seems not to be strong enough. The bus still has to wait and we are still stuck. But we think we are in a fully occupied bus, we are already late, and we think, okay, actually we would like to have a stronger prioritization because so many passengers would benefit from that. We expect that in the next years with vehicle-to-X communication, it will be possible to transmit occupancy and delay as an additional information for the control, so that prioritization can be adapted and considering delay and occupancy so that the bus is prioritized stronger and earlier and more flexible. So we are considering this future scenario in which the bus prioritization is not first come, first served as it's done normally today. So normally when a bus is recognized, the first bus that is recognized is also prioritized. But we want to use the information from vehicle-to-X communication to make a more flexible control, and maybe then a new bus appears that should be prioritized before the other bus because it has a higher delay occupancy. And as very essential for that is the estimated time of arrival prediction. This should be very accurate. So we will have different priority levels in our prioritization, and those determine the starting time of the prioritization, and therefore also like how big is the intervention of prioritization in our normal traffic signal control. And we also investigated how could the practical assignment of priority levels look like based on the delay and occupancy. I already mentioned it a little bit, so the bus prioritization is then based on the estimated time of arrival and has to be scalable based on this estimated time of arrival. And it's also very important that our bus prioritization is flexible and easy to adapt, because when there's a new bus appearing that has a higher priority degree, then this should be prioritized even before we might even have started with another priority procedure. So what is the timetable for today? In the next slide I will start with the methodology, including the prioritization logic, levels, the control strategies, the simulation scenarios, and then finally I will show you the results of some test simulations and also mentioning the limitation, next steps, and the summary. So what is the methodology in this work? So we have simulated a subnetwork of the SUMO network of Ingolstadt. This network is publicly available. Here you can scan the QR code on the right to access this repository. We had the so-called Kiwi project running in Ingolstadt for artificial intelligence in the traffic system of Ingolstadt, and this motivated our work. So we simulated this subnetwork of Ingolstadt and applied the bus prioritization at this single intersection, but we also wanted to have the impacts of surrounding traffic shown in our test scenarios. So how does it work in detail? During simulation, we always know which buses are in the system, and if we imagine that in reality, with vehicle-to-X communication and roadside units, we will always know everything about our buses. They should transmit their position, their line, their occupancy, and also, of course, their delay. And for every simulation second, we check again which is the bus that has to be prioritized. And as I already mentioned, this can also change. So, but how to decide which bus should get the prioritization? First, so as I already mentioned, we have delay and occupancy considered. The delay is categorized from A to E, with A being the highest prioritization, and the occupancy is leveled from 1 to 5, with 1 being the highest priority, and combined we receive levels like, for example, A1. So at first we assign the current delay of the bus in the levels as shown here. Here you can see some example values. After we assign the delay level, we assign levels for the occupancies. If a bus is in the same delay level like another bus, the occupancy decides which bus should be prioritized first. And in the end, we have different priority degrees. Those priority degrees decide at which time the prioritization should start. And also, of course, therefore, also how strong the intervention is actually in traffic signal control. So when you have level E in the end, we don't make any prioritization. When we have level D, then green time has to be ensured at the estimated time of arrival of the bus. When we have level C, green time has to be ensured at estimated time of arrival minus 10 seconds, with B minus 20 seconds. And when we have the level of A, then the prioritization has to be immediately started. So I already mentioned those different levels, green as soon as possible at A, and then based on the ETA value, we have the other priority levels. So here we have the decision when to start the prioritization, but then in addition, of course, based on what is the current phase that is on and the desired phase, we also have different strategies in the control, how to ensure the green time at the desired time. And we have green extension, red truncation, and red truncation extended for that. On this slide, you can see how this works. So here, the current phase is also the desired phase, so we stay in the phase and extend the green time. For red truncation, our current phase is not the desired phase, so we terminate the stage earlier, of course, ensuring that still the minimum green times are kept, and then switch to the desired phase, and add red truncation extended. Also, the current phase is not the desired phase, but there are other stages in between. So we end our current stage, and also for all the follow-up stages, we only have the minimum green time so that we arrive at our desired phase in time, and not also in time, also in the time that it should be supposed to be, like based on the priority levels that we assign. So I already mentioned that the estimated time of arrival is a very important parameter, and it has to be a very good prediction to have a good prioritization. So we check for every bus what is the route of the bus and what is the current location and distance to intersection. And then, of course, it has to be considered if there is a bus stop in between or not. And it's very important also to have good speed values for that. So if there is not a bus stop in between, we take the current distance and speed data that we have learned from previous simulations to have a good estimation for the ETA. And also, if there is a bus stop in between, we also learn from simulation and see what was the service time at the last bus stop, and of course then what is the distance to the intersection, and what is normally our average speed at this intersection approach. When we have decided what is the priority of our bus, the priority degree, and when we have decided, okay, what to do to ensure the green time at the desired time, we check again every second if our ETA value is bigger or smaller, the maximum switch time. The maximum switch time is the maximum amount of green time that we need to switch to the desired phase, and plus the time that it is supposed to start earlier based on our priority degree. If the value is higher, we still again check our priority scheme and also check if another bus should be prioritized at a higher level. And then if we have reached the ETA value to act, then we start with our priority procedure, and then the priority ends as soon as the bus has crossed the intersection. There are so many different test scenarios that are possible to test the control that I have shown to you. We decided to test 4 different scenarios in 2 different demand levels. So on the one hand, we have the rush hour from 7 to 8 a.m. and then we have like an off-peak traffic from 10 to 11 a.m. And on the one hand, we tested the situation that the buses like appear and at the same time, and then that they also arrive at different times. We have scenario 1. Here you can see with the arrows indicated the directions of the buses. Here the buses have the same priority level A, but they have a different occupancy, and then the occupancy decides over which bus has to be prioritized first. Then in scenario 2, we have also the same registration time, but different priority levels. Then at scenario 3, we have different registration times and different priority levels. And scenario 4 is actually the same as scenario 2, but in the off-peak hour. Now let's take a look at the results. We have simulated every scenario by 13 simulation runs, and then we also simulated a non-prioritization scenario, so to say, to have a better comparison how effective the prioritization is. In green, you can see scenario 1, where we have a bus prioritized and the other bus is not prioritized. You can recognize that by the P and the N, P prioritization, and this bus cannot be prioritized just because they really arrive at the same time. Normally, and maybe a bus has a bus stop in between, and then of course the second bus can also be prioritized. This is really the situation that the second bus is arriving at the same time at intersection, so that only one bus can be prioritized. We see that we have huge improvements for the prioritized buses. The prioritized buses can save up to 56 seconds, equal to 87%. But on the other hand, of course, when it's not possible to prioritize the other bus, this bus has an increase in travel time by, for example, here in yellow, 18 seconds. But overall, in absolute terms, the improvement for the prioritized bus is higher than the deterioration for the non-prioritized bus. Then we have simulation scenarios where the bus is already kind of using the green time, so we only have very small improvements of travel time here. So here actually the bus prioritization doesn't have a huge effect, but we observe something interesting, that also the non-prioritized bus has a reduced travel time. This is because the strategy that we chose in this situation, the red truncation extended, was used by the non-priority bus also to get green time and then to cross the intersection. Let's go on to the number of stops. Here we observe similar things. So we have huge improvements for the buses that are prioritized. So we have here the average value of our 13 simulation runs, and here the number of stops is reduced to 0 for this scenario, for example, and here it's also improved a lot. On the other hand, of course, for the non-prioritized buses, compared to a scenario without prioritization at all, we have a deterioration, but overall, again, in absolute terms, the improvement for the prioritized buses is higher than the deterioration for the non-prioritized buses. And we see also similar things like we did with the travel time. Here for the prioritized bus in scenario 2, in that case, there is no improvement because we already have a good situation traffic signal control-wise for the bus. The bus is lucky, so to say. But on the other hand, we also see that here the prioritization does not have any effect. This is because the bus is left-turning here, and the bus is has to wait for the other left-turning vehicles downstream. Therefore, the prioritization does not have any effect. It would only have an effect if we introduce an additional stage phase for our buses, for our left-turning buses here. Let's take a look at the queue length. So here we compare scenario 2 and 4, which is actually the same situation, but once in the peak hour and once in the off-peak hour. Here is the start of the prioritization, and we can see that our prioritization has an effect. So the prior bus is the blue one on the western approach, and the queue lengths go down on the western and the eastern approach, and at the same time, of course, they go up on the opposing direction. So on the north and southern approach, the queue lengths go up. And what we also see, that of course this is also something that we would expect, that the queues stay still quite small in the off-peak scenario, but in the peak scenario they go up faster again. So we have a 1.2 times increase in the queue length compared to a non-prioritized scenario, and a 5 times increased queue length compared to a non-prioritized scenario in the off-peak hour. So overall, here you can also see how fast we return to normal operation again, and also like what we would expect in the off-peak hour, we have a faster return to normal operation. But in general, we showed also, like taking a look at this queue length, that we managed to implement a prioritization that is very effective, but at the same time not disruptive too much for the other intersection approaches, so that we ensure a fast return to normal operation and not that of big disadvantages for the other intersection approaches, which is always an important aim in bus prioritization, to give them priority but not to have too many disadvantages for the other directions. Okay, so what would be our next steps? So I presented our approach to have an accurate ETA estimation. How could we improve that? The next thing we would like to try there is considering real data. Here we learned from previous simulation runs to have a good average speed estimation, and also to know how long the bus will stop at the bus stop. But of course, this could be improved by using real data. So this would be the next step. Of course, we also tested different scenarios that I haven't shown here. But overall, there are so many scenarios that could be tested to further improve it, especially when we extend the prioritization to the network. What would be our next step? I have shown a prioritization at isolated intersections, but we expect that if we coordinate the prioritization at kind of in the network or along a stretch of intersection, that then we can control the platoons of the vehicles even more and have bigger improvements of the prioritization than we already have. So to sum up, the aim was to test or show the feasibility of a prioritization that is not first come, first served based, but adapts always to the situation. So if there are other priority buses appearing that have a higher priority level, the situation is continuously adapted to that. And this is possible with V2X communication, which we expect in the near future scenario. We have shown how this priority degree assignment could work based on occupancy and delay. And we have also shown what those prioritization degrees could mean for the timing of the prioritization based on the estimated time of arrival. And then finally, we showed some test scenarios at which we observed the high reductions in travel time, stops in queue length for the prioritized buses, but at the same time we showed that the negative effects on overall traffic is not that high. So if the situation appears that we have a bus that could not be prioritized, that still then the bus doesn't receive big advantages and only temporary negative effects. If you imagine there might be intersections that are really close, for example, to a main station, something like that, there it could be the case that really many buses arrive at the same time, and then of course you don't want to have that big of disadvantages for other buses. That's it. I'm looking forward to your question. Thank you for your attention.